Hello, everyone. Yeah, I'm Martin Braun from Edis Research. We are a diamond sponsor of this conference, and we have been a sponsor for the last 9 conferences. So since the beginning, I'm very proud about that. And as such, I'm also happy to be able to be here and represent, the makers of the USRP. So last year, I also gave a talk in the same capacity. It was a bit more forward-looking. I had some questions in there. I'm going to do none of that. This is just going to be straight-up stuff that we built last year. I'm going to show it to you. There's another talk on Thursday, which is a little bit more roadmap-y, but this is just features. And I'm going to go start with things that we built last year that you might be interested in. And what do we have here? So this is the N320, our latest USRP in the USRP product family. It is sort of the fastest and widest bandwidth that we've built so far. It comes in 2 varieties, N320 and N321. The difference is the fact that this USRP has a unique new feature that we haven't had as such in the past, which is the ability to actually share an LO between up to 128 channels. So when you're doing synchronization, LO sharing is kind of the gold standard for achieving phase coherence. And the way this works is you build a 4x4 grid of N320s. You kind of share an LO through each column, have sort of a master in there. And then you pick another one as a grandmaster who will then serve each 4x4 grid. That's how you can synchronize up to 128 by 128 channels in a MIMO fashion. Other than that, it has a couple of other really interesting specs. It has the widest tuning range that we have so far, 1 megahertz to 6 gigahertz, and also the highest rates and bandwidth. So 200 megahertz of instantaneous analog bandwidth available through the 250 mega sampling rate. It also does 200 and 245.76 mega samples for your Wi-Fi and your LTE rates. And in order to get all the data off the device, we've put it in the same enclosure, kind of, as the N310, but it has an extra QSFP port for extra data transport. So you can have, for example, 2 10 gigabit links to your device and still have another one for White Rabbit and management and control. And because it comes in the same enclosure as the N310, it also has the same management and features. It has an embedded Linux system running on it, which you can use for all sorts of fun stuff. So as such, it fits really nicely into our product family here. So from less to more expensive here, but really the column you might be interested in depends very much on your requirements. And then we're sort of very happy that we can meet so many different requirements at this point, from very flexible with the X210 and the swappable daughter boards, the form factors that the embedded series has, and of course the really high rates that the N320 has. We actually have a booth right over there, so you can look at some of those USRPs and check them out. So I mentioned the high rates. In order to achieve that, we actually published something else this year as part of our UHD driver, which is a DBDK stack. A DBDK, I don't want to go into too much detail here, is a networking layer that allows us to sort of take over the control from the kernel, say, hey, kernel, I need that network card, back off, and then we sort of handle the NIC controls ourselves within UHD, which is something you can use with our X series and the N300 series, which is really useful if you want to achieve those high rates reliably. Okay, so this is stuff that we published, but we've actually been working on a lot of other stuff, and I do want to let you into some of the things that are imminent. So the reason, sorry, I skipped over this here. The reason I wasn't going to go into too much detail here is because there's another talk on DBDK on Wednesday. Yes, software roadmap. There's a couple of things that are coming in that you might be interested in. So UHD is the USRP hardware driver. So that's the driver stack that we use to drive our series. And there's another release imminent later this year. 3.15, it will be an LTS branch like we had with 3.9. So this branch will be there for a while, and we're going to keep adding bug fixes to it. There's no actual products or features tied to it. This is just a stable branch that we want to keep around. One major thing that you might be interested in is that RFNOC is now enabled by default, which means if you install our binaries, it'll now just have RFNOC coming with it. And if you look at our current master branch, you will have a pretty good idea what's coming on this release cycle. However, slightly more excitingly, we also have UHD 4.0 in the pipeline. That's something I've been waiting to be able to talk about for a long time now. Finally bumped the 3 in the first time. In fact, the first release, stable release of UHD was 3.0. Like we never had a 1 or a 2. So this is a big change. Timeline for that is early next year. However, you can also look at this UHD release. Even if it is bleeding edge, I would not recommend it for like any kind of stable, implementation. The reason we are publishing a bleeding edge branch here is because we want to give you the opportunity to see what's coming up. In case you are interested in the new architecture that we are building. This is a massive change in terms of lines of code. I know they aren't really a useful metric by themselves, but compared to other releases, this is really big. Why is it so big? Because we have touched the basic thing that ties all of our use groups together. We've touched RFNOC itself. So UHD is the driver for all of the overall driver that you interact with, and RFNOC is the underlying architecture that tells us how we program our FPGAs, how we get packets on or off the devices. Why on earth would we do that? Quickly, one thing I want to mention, because now we get into sort of a bit of a naming issue, like what old RFNOC, new RFNOC. So I'm going to refer to what is in 3, like in all the stable branches, we're going to Pro RFNOC, and then what's coming in UHD 4.0 will be called RFNOC. Why on earth would you touch that? Why would you rewrite something like RFNOC? There's a couple of important reasons here. The first one was rates. I talked earlier about 250 megasample rate. In a dynamic and flexible architecture like RFNOC, we've kind of maxed that out. We can't really go much faster without doing major changes. So we said, well, I guess we're going to have to do major changes here just to achieve higher rates. Another thing about RFNOC is the point of RFNOC is the ability for you as the user of the USRP to put in custom features onto the device. Filters or modems or whatever you want. We use that ourselves, like for the digital down converters, like the resamplers. We all use RFNOC, add editors, to implement these features. And a common complaint or request was like, can we add more blocks? Because in the current design, it's somewhat limited. We said, sure, we can do that, but that'll also mean big changes, not just on the FPGA side, also on the software side. And the current design is kind of simple. There's a crossbar, and you can connect blocks to it if you're familiar with those terms in RFNOC plan. But that is another way of saying there's not a lot of design choices you can make. So we thought, okay, we need to be able to give people more design choices to use the limited FPGA resources more efficiently. And putting it all together, we don't want to make it too complicated, so the user experience is also very important to us. So what did we do? The first thing we did was we leaned back, went to the whiteboard, and then spec'd this whole thing out. This took a long time, and we published a document on that URL. I actually have 3 hard copies of that. If someone's interested, I have some to give away. Planning it all out. It was a very important first step, just to collect all the user feedback that we've gotten, not just from external, but also just like from our own internal processes. And then we started writing code. And there's so much change in here that I can't possibly cover it all in the time frame. However, I will give you some of the highlights. And for example, this is what it kind of looks like on the FPGA now. Those of you who are somewhat familiar with RFNOC will recognize some things here. In an FPGA design, there's a bunch of blocks that implement various modules of the things that you want to implement, like FFTs and filters. So they're on the right side here. And in order to plug them into our architecture, you needed something what we call the NOC shell. So you took an AXI stream compliant IP, put it in a NOC shell, and then you were able to put it into RFNOC. That is still all there. Hasn't changed. However, the NOC shell has been stripped down significantly. It is we took everything out that made it slow and high resource utilization to be able to put in way more blocks than we had in the past. There's 2 things that are new here. One of these things is a control crossbar. We realized that for control traffic, you need to be able to talk between all of these potentially hundreds of blocks if your FPGA allows you to put that many down. But you don't need like the highest throughput on this end. So this has its own custom crossbar for control traffic. And another thing that is new here is what we call a static router, which is really just a fancy way of saying instead of connecting all of your blocks directly to the crossbar, you are now also able to statically connect blocks if that's what you need, because that might give you a better latency between blocks, and it might also give you a better resource utilization. Now I mentioned earlier we stripped down the NOC shell, but we didn't put junk in the NOC shell to start with. So the stuff we took out of the NOC shell, we had to put somewhere else. So the next concept I want to introduce here is stream endpoints. A stream endpoint is something that can marshal traffic in a, in a way that is not an axis stream connection. So one thing you'll notice here is that we have fewer stream endpoints and we have blocks on the right-hand side. And that's because we have some of the blocks statically connected. Finally, our good old friend, the cheddar crossbar, is still in there. This is where data gets routed around like arbitrarily. We also worked on this to increase the throughput and to be able to hit higher rates that we want to achieve in the future. So let's look at an example application here. So let's say you want to do something spectrum analysis like. So I'm going to give a very simple example. Let's say you have an FFT and a radio. The radio is just another block like any other block, except it also has IOs connected. And because we are confident we never need the actual samples in this particular design, we will choose to directly connect the radio to the FFT. And then the FFT does its math, and then we get the FFT bins sent home to software through one of those stream endpoints. So we have a static connection that goes like this, a static connection that goes like this, and then software is able to talk to the stream endpoint and get the FFT bins out. Control traffic, on the other hand, which comes from the software, will also go to the stream endpoint, gets marshaled elsewhere to the control crossbar, and thus gets distributed to the individual blocks. So we have no downside by the fact that we put the radio behind the FFT from a data streaming perspective. Now let's say we add a spectrum sensing block in there. Or let's say you add a spectrum sensing block in there. What can we do here? So let's say we're really confident that we're never going to need the FFT bins either. We just want whatever the spectrum sensing block outputs. So we'll do another connection like this here. And then the spectrum sensing output could be, maybe it's a trigger or something like that. Will give us samples, FFT bins, or whatever it is that it calculates. However, it could also do something else. It could send control traffic to the radio. So it might just be a pass-through. Since all of these blocks are on the control crossbar, they can exchange control traffic easily. So this is also a feature that we've retained or even improved. But what if this guy isn't working? So spectrum sensing block is not doing the right thing, but your test benches are fine. You're like, something's going on. I'd like to run it on hardware. You don't have to connect it directly to the FFT. Like, we didn't actually take away anything from the original RFNOC. We just added design choices. So you can also put the spectrum sensing block on its own stream endpoint, send it test vectors, see what comes back, and thus debug your design. And on the same FPGA image, you can also route traffic through the cheddar crossbar, because that's something we also supported in all RFNOC. The only difference between this and the direct connection is that you now increase your latency by a couple of pocket cycles. So we also had a lot of software changes coming with this. So for example, consider, this is just an example where we string back to back a couple of blocks. But if you look at the properties of these blocks, they all have an FFT size. So we need to make sure that they're all the same. Now in Uniradio, this is not a very difficult problem to solve. You would just simply source the property from the same variable, change it all that way. However, with UHD, we went a step further, which is UHD internally tracks like the graph connections that you chose, the way you wanted to stream data between your blocks, and it itself also makes sure that any kind of properties that are relevant to your connections stay consistent. And for that, we introduced what we call a graph propagation framework. And I'll give you a very specific example of how that works. So let's take this very simple case here. You want to look at data at a very specific rate. And let's say the DDC itself has one register called decimation word, which is defined somewhere in software. We have two edges here, and those edges also have properties, which are, in this case, the sampling rate. So the property propagation framework will make sure that all of these properties stay in sync with each other. So in order to do that, you define little snippets of code that simply declare the relationship. So in this case, the output sampling rate is the input sampling rate divided by the decimation. And if you say, okay, I would like on this output, I would like this sampling rate, then UHD will internally make sure that that condition can either be met by programming the registers accordingly, or if that's not possible, giving you an error message. There's plenty of other features that we added to RFNOC. I really can't list them all here. I just want to go through a couple of highlights here. We retained the multi-user compatibility. We're kind of de-emphasizing the property tree because we have way more C++ APIs now that give you more type safety both at compile time and at runtime. We've also pulled out the motherboard control from the block controllers. So in this case, this is a new radio representation of the good old UHD source. And the bottom half is an equivalent implementation in RFNOC, where like the motherboard controls are in a separate block, and you have the radio to DVC, and then going to the host, you have to stream them. So yeah, there's plenty of other things in here. Now, I know I only give you some of the highlights here, but a very important question, like now that we know like what the FPGA and the software can do, is like how can people actually use this? Because this is not something we made to make our own lives easier, although well, that's actually exactly what we did. But we also wanted to make your life easier, because the whole purpose of buying a device with a big FPGA is being able to program it easily. So in the Santa Clara office, whenever I have a question that pertains to FPGA programming, I always ask Suganda, who's right here. So I'm going to do the same thing right now. Maybe you can like give us some idea about the tooling that we did. I'm just going to close the mic. Oh, sorry.
So apart from all the software changes that we had, we also made updates to the tool flow. And we still have the same RFNOC image builder and the block tool, but we did make updates to them to support UHD 4.0. But the most exciting update that we did was actually add the ability to generate your FPGA images using GRC. So let me show you how that would work. So this is how you would visualize the FPGA image in GRC. And this is a typical default FPGA image of an X310. On the right side, you can see here, this is the X310 DSP, which has different ports. It has like clock domains, it has CE clock, radio clock, it has the I/O for the radios, and it also has connections to the stream endpoint. What you see on the left side are these static connections. These blue arrows are the static connections between DDC, radio, DDC, and they're connected to two stream endpoints on slot A and the same thing on slot B. Now, let us say I want to add an FFT to my FPGA image. So I just search for FFT block, and then I search for a stream endpoint. And connect them. And what this does is it adds an FFT as a dynamic connection on in your FPGA image. And if I want to add it to a static connection, then I can just remove this connection and add it in one of the static chains. And that's how easy it is to build an FPGA image now. So let's see how this would look like for a typical FPGA developer or a block developer, as I said. So we have the block generation tool. You as a user will have to provide all the details that you have you need in your block, the number of ports, if it has any I/O ports, and put it in a YAML file, which gets used as an input to the block tool. It generates a block-specific NOC shell for you, NOC block template, where you add your user IP, your custom logic that you have, and it generates a test mention where you add tests for your settings. The YAML file gets added to a block database, which has other blocks that we provide as well, and then you can use it for your FPGA generation. This YAML file right here is a block level, is an FPGA level YAML file, which basically where you can tell what topology you want, your blocks to be connected in, what all blocks you want, or you can also use the GRC, but you're not limited to it, and you can use the YAML file as well. And it will pull in the database from the block database, and which gets fed into the RFNOC image builder, and you generate the bitstream as usual. And then you load it into your user, and then the user application is sorted.
So Suganda showed us a little bit about how we build applications. I also brought a friend here who's been working a lot of using RFNOC from an application perspective, and show us what we have. Like, how can we actually use it as an end user?
Sure thing. So as Martin mentioned earlier, the multi-user user experience shouldn't change very much at all with this RFNOC redo. That means the GR will largely remain the same. However, GR-edis, our out-of-tree module, will change. And I'd like to just go over a couple of flow graphs to kind of demonstrate some of the changes. So here is a pretty basic example that we have. If you've used GR-edis before, you'll notice that the radio and the DDC are pretty much the same. They have slightly different options now, but this new RF streamer block is a real big difference here. And so we've created streamers to match the underlying RFNOC API a little bit more. So we didn't really talk in depth about the C++ API that we provide, but you'll have to now call connect between blocks and streamers, and we wanted to reflect that in new radio as well, give people a little bit more control. This also has the benefit of solving a couple performance issues we had in proto-RFNOC. For example, now in GNU Radio, if you wanted to have a single computational block running, your streamers will have their own threads allocated to them by GNU Radio, and so any performance issues related to that particular case have been solved. Additionally, we've also given a little bit more control over what exactly is going to be time and phase aligned. So say instead of one large DDC block, you wanted to have it separated into two and make sure that those two blocks were time aligned. Now, with this new RF streamer block, those sample streams would be. So now I'd like to just show a quick example of something that we got working recently for this. So this is a loopback sample. Let me just zoom out a little bit to show the entire flow graph here. It goes from the RX radio to a TX radio, and you'll notice that all of the data path is in the FPGA. We don't have any hosts touching this, which is exciting because this wasn't possible in proto-RFNOC. This is a new feature that works just straight out of the box with the new RFNOC. So what I'm actually doing here is I have one USRP X310, which is taking in a signal, and that's transmitting those samples over an Aurora link to another X310, which is then transmitting it. And we just have a signal generated and input, and then I'm comparing the input and the output to do a basic measurement of latency between those. You can kind of see that in the bottom right. We have the oscilloscope and the measurement there. But what's really important here is that this is a brand new feature that will work out of the box. So the real takeaway here is that we want this experience to be as similar as possible between our C++ API and GR-edis. That is, if you know how to build a RFNOC flow graph in one, you know the steps to create in the other. It should be easy and simple for everyone to use.
That is a small glimpse from us into like what we have to, the pipeline for the immediate future. I don't know, we have time for a few questions maybe. Okay, excellent. Well, thank you very much.